Hello everyone. Today we are learning about ions and bonds. First of all, atoms are more stable when their highest energy level is filled with electrons. So how many electrons does it have to be full? Well, the first energy level is full when it has 2 electrons. Only 2 can fit in that small first energy level. But in the second energy level, you can have up to 8. The third energy level can have up to 18, but it's stable with 8. The fourth energy level can have up to 32, but it's stable with 8. And the fifth energy level can have up to 50, but it's stable with, you guessed it, 8. Atoms like to have 8 valence or outer electrons. That's sometimes called the magic electron number because that's the perfect number that they love to have. It makes the atoms more stable, less reactive. So let's take a look at how they get those electrons. Here is a list of valence electrons in each group in the periodic table. This group always has 1 outer electron. This group always has 2. 3, 4, 5, 6, 7, 8. You get the idea. Now here's how this works. Hydrogen has 1 outer electron and 1 electron total. Helium has 2 outer electrons, so it doesn't quite have 8, but remember that first energy level is smaller and it's full with 2. So helium is still very stable because it already has the correct number of electrons and doesn't want to react. Reacting means either gaining, losing, or sharing electrons. It doesn't want to do that because it already has the perfect number. So notice hydrogen, helium, 2 atoms in this row or period, 2 electrons in the first energy level. All right, lithium has 3 total electrons, 2 in the first energy level, 1 in the second energy level. Beryllium has 4, 2 in the first energy level, 2 in the second. See how that works? All right, neon has 10 total. 2 in the first energy level, 1, 2, 3, 4, 5, 6, 7, 8 in the second energy level. All right. Sodium has 2 in the first energy level, 8 in the second energy level, and 1 in the third energy level. Notice how hydrogen, lithium, and sodium all have 1 electron in their outer energy level. All right, so it continues on like this and makes it fairly easy for you to figure out how many electrons are in each energy level. Now let's look at what charge each ion will get. Hydrogen, lithium, sodium, etc. have 1 outer electron, and they would like to lose that electron. For example, sodium wants to go back and have 8 outer electrons like neon does. So it loses that 1 outer electron and ends up getting a positive 1 charge. Now, wait a minute. It loses an electron and gets a positive charge? Remember, electrons are negative. Losing a negative is like subtracting a negative, which gives you a positive charge. These like to lose 2, so they get a positive 2. Notice below the stair-step line is where all the positives are, below and to the left. So aluminum gets a positive 3. Then above and to the right of that stair-step line are the negative charges. Boron has 3 valence electrons, just like aluminum does. Aluminum likes to lose 3 to become like neon. Boron likes to gain 5 to become like neon, to have those 8 valence electrons. Carbon had 4 valence electrons, negative 4, gain 4 electrons. Why is it negative? Because electrons are negative. And if you gain 4 negative electrons, you become more negative. Nitrogen has 5 valence electrons, so it wants to gain 3 more to become like neon. See how nitrogen, 1, 2, 3. Oxygen has 6 valence electrons. It wants to gain 2 to have 8. Fluorine has 7 valence electrons. It wants to gain 1 to have 8. So that's what we mean when we say that they are more stable when their highest energy level is filled with electrons. Either, if it's the first energy level, it wants 2 electrons, and if it's the second, it wants 8. Then if it's the third, fourth, and fifth, they are also stable with 8 valence electrons. So Lewis dot structures are a faster way of drawing atoms and ions because they only show the valence or the outer electrons instead of showing them all. So for example, let's draw the Lewis dot structure for carbon. We find out how many valence electrons carbon has. Here's carbon. It has 4 valence electrons. So we draw 4 dots to represent the 4 electrons. Now the key is you cannot pair the electrons until you have to. You have 4 sides. You have top, bottom, left, and right. And so you want to put each electron in a separate location when you draw that Lewis dot structure. Magnesium is here in group 2A with 2 valence electrons. So we draw 2 dots. You cannot draw them together. You must draw them separately. You can draw top and bottom. You could draw side and side. You could even draw top and side, bottom and side, any combination you want, except you cannot pair them. This is wrong. The others are correct. All right, oxygen. Oxygen has 6 valence electrons. So we do 1, 2, 3, 4. Wait a minute. Now we have to pair them. There's no more room. So I'm going to pair it at the top and the bottom. It's okay if you put the pairs at the sides or at the top and the sides or the bottom and the sides. What you cannot do is make 3 pairs. That would be pairing them before you had to. You try nitrogen. Pause this video and see how you do. So for nitrogen, we have 5 valence electrons. So we do 1, 2, 3, 4, and then finally pick one and pair it. You try lithium, fluorine, and neon. So here is what the Lewis dot structures should look like for lithium, fluorine, and neon. Notice neon had to have all pairs because it has 8 valence electrons. Atoms whose valence shells are not full will gain or lose electrons to have 8 or 2 valence electrons so that they will be stable. So for example, nitrogen has 5, it's going to gain 3 more, so it will have 8. Lithium has 1, it's going to lose that 1, so that back on the inside there are still the 2 electrons. Remember, lithium only has 3 total. Back on the inside it has 2 like helium does. When atoms gain or lose electrons, they get a charge, and they are ions. Ions have a charge, atoms do not. Ions are atoms that have gained or lost electrons to get a charge. The superscript to the upper right of the ion formula is the charge. It goes with the entire ion, and it must have a plus or a minus. You can't just have a number. It's not like math, unfortunately. You do have to have the positive or the negative. If there are subscripts are down at the bottom, they tell how many of each atom there are. And you don't ever write 1 as a subscript, because if you just have 1 atom, it's assumed that you have 1. Remember, superscripts go up in the air like Superman flies in the air. Subscripts go down below like submarines go underwater or subways go underground. So we already have the charges on the ions and show the Lewis dot structure of the atoms versus the ions. So we've already drawn the Lewis dot structure for carbon. Now let's draw the Lewis dot structure for the carbide atom. Remember, all negative ions have to change the end of their name to "ide." So carbon has gained 4 electrons. It already had 4, it's now gained 4 more. So instead of 4 electrons, it now has 8. And they all had to be paired because there wasn't enough room otherwise. Now we need to put the charge. What happens is we need to move this charge. We put squared off brackets around an ion, and we put the charge outside as a superscript, up in the air like Superman. So that's how the ion should look. Mg plus 2, let's see, it's backwards. Plus 2 meant lost 2 electrons. Originally, magnesium only had 2 outer electrons, and it's lost them. Instead, magnesium has lost 2 and it now has 8 valence electrons like neon does. There's 2 in the first energy level, 8 in the second, and the third is now empty. So magnesium had 2 electrons, lost 2. You can either draw no electrons because that third energy level is now empty, or you can draw 8 electrons to show it's now like neon. But I personally think it's way easier to just draw nothing. And that's part of why you put the brackets around here, is because how do you know you meant to draw nothing? Well, if you put brackets, you'll know, oh, it's deliberate, there's nothing inside the brackets. Take this positive 2 and move it outside as a superscript up in the air, and that's your magnesium ion. You try oxide, remember oxygen becomes oxide because it's negative, nitride, another negative ion, lithium, notice the name doesn't change because it's a positive ion, and fluoride. Oxygen had 6 valence electrons, negative 2 means gain 2, so now it has 8. Don't forget the brackets and move the negative 2 outside. Nitrogen had 5 electrons, it gained 3, so now it has 8. Do you see a pattern here? They all like to have 8 valence electrons. Lithium had 1, positive 1 is lost 1, so now it doesn't have any in that second energy level. Yes, there are 2 electrons back on the first energy level, like helium, but we don't have to draw those. So we put brackets to show that we're drawing nothing, and move the positive 1 outside the brackets. Finally, fluoride had 7. Negative 1 means gained 1, so once again, it now has 8. This is why these ions are much more stable than the original atoms, because they now have the magic electron number, the perfect number of electrons. Remember, a negative ion is an anion. It is a negative ion. See how that will help you remember? So this is the carbide anion, the oxide anion. You get the idea. A cation is a positive ion. Remember, cats are positive. I like cats. If you don't, just remember, I like cats. And so these are positive ions. So this is a magnesium cation and a lithium cation. Now let's look at what happens when 2 atoms join together to make ions. Ionic compounds form ionic bonds, and they do this because they make ions. One atom will lose electrons and one will gain. I've color-coded these so you can tell which electron originally belonged to which atom. So for example, sodium had 1 valence electron and chlorine had 7. As you'll see, sodium has 1 valence electron, chlorine has 7. Sodium would like to lose 1 electron and chlorine would like to gain. It's the perfect match. So sodium gives away its electron to chlorine, sodium becomes a positive ion, and chlorine atoms become a chloride ion with a negative charge. Then, now why do these stay in a bond? Sodium has given away its electron and it's not taking it back. Chlorine has taken the electron, it ain't giving it back. So why would they even stick around each other? Because opposites attract. This is now a sodium ion with a positive 1 charge. And this is now a chloride ion with a negative 1 charge. And opposites attract. And that charge is what causes them to be attracted together. All right, let's look at magnesium and chlorine. Chlorine had 7 valence electrons, magnesium had 2. So chlorine's like, give me an electron. Magnesium says, okay, here, take 2. I only want 1 electron. Well, what am I supposed to do with this other one? It finds another chlorine and gives the second electron to the other chlorine. Therefore, to make this work, you have to have 1 magnesium and 2 chlorine atoms, or ions. So this is magnesium chloride. We have one magnesium and two chloride ions. This is sodium chloride. We have a single sodium and a single chlorine. Notice how I put a subscript to tell you how many chlorines. Is this the charge on the chlorine? No, it had a -1 charge. But it took two chloride ions and one magnesium ion to make the perfect match. So a single magnesium, notice do not put a 1, and two chlorides. The subscript at the bottom tells how many chlorines. The superscript at the top tells the charge on the ions. Notice I don't put a charge in the formula. Here we had one sodium and one chlorine, so we have one of each. We don't put any subscripts because you don't ever put a subscript of 1. And there's the formula for sodium chloride, which is table salt. All right. Molecules occur when both of the ions want to gain electrons. So it's not the nice match like it is here. This one wanted to lose, this one wanted to gain. It's perfect. Here they both want to gain. We have a problem. So this fluorine has 7 electrons, and this one has 7. And this one says, hey, give me your electron. You give me your electron. No, you give me yours. So they finally agree that they're going to share the electrons. They get really close to each other. You can see that I've color-coded it, and you can see by the circles here, this fluorine now has 8 electrons, and this one has 8. They do that by sharing these 2 electrons in a bond. So here I've color-coded it. This is how you would actually draw it, except you don't have to color-code it. And then these circles show more clearly which electrons belong to which atom. Although you don't actually draw these circles in your answer. Here's another example. Hydrogen would like to be like helium. It would like to have 2 valence electrons. Oxygen would like to be like neon. It would like to gain 2 more electrons, and hydrogen would like to gain 1 more. So they fight it out. They say, all right, give me your electrons. No. And so they end up sharing. The hydrogens come up close to the oxygen. The hydrogen and the oxygen share these 2 electrons. One came from the oxygen, one came from the hydrogen. This hydrogen shares the electrons here with this oxygen. And then oxygen still has 4 non-bonding electrons that belong to it alone. So the oxygen has 8 total, 4 that belong to it and 4 that are shared. And the hydrogen has 2 total, just like helium. It wanted 2 electrons. So that's the difference between an ionic compound and a molecular compound. An ionic compound, one wants to lose, one wants to gain, so they give and take electrons. With a molecule, they both want to gain, and so they share electrons.